After we have the arrow analysis for the Gauss-Seidel iteration, we can also use the eigenvalues of the Gauss-Seidel arrow matrices to evaluate the stability and the convergence. Okay, so let's compare with the Jacobi and the Gauss-Seidel iterations. For the Jacobi iteration, just to recall what we have derived before, this arrow k plus 1 will be equals to negative d inverse L plus u arrow k. So this is the arrow for the next looping, and this is the arrow of the current looping. And this is the matrices if we get the eigenvalue, if the eigenvalue lambda maximum. So the absolute number of lambda maximum, if that is all smaller than 1, then the Jacobi iterations can work and converge. If one of the lambda maximum, if the maximum is over 1, then the Jacobi iteration won't work and the system won't converge. Okay. For the Gauss-Seidel iteration, the arrow we just derived k plus 1 will be equals to negative L plus D inverse U arrow k. So the next iteration arrow will be equals to the arrow matrices times the current arrow. And if similarly the eigenvalue of these matrices, if the maximum absolute number is all smaller, the maximum is smaller than 1, then that means my Gauss-Seidel is converged. And the Gauss-Seidel iteration can work. If the maximum is over 1 for the absolute number of the eigenvalues, then the Gauss-Seidel iteration won't work and it won't converge. Okay? Then let's draw a picture regarding the Jacobi iteration and the Gauss-Seidel comparison. So if I have this a 2D the 2D plot, usually the Gauss-Seidel eigenvalue will fit in this circle. Okay, usually the Gauss-Seidel iteration will fit for this circle, while the Jacobi will fit in a bigger circle. So this is the Jacobi. Okay, Jacobi iteration. The eigenvalue is inside this circle. The Gauss-Seidel is in a smaller circle as compared to the Jacobi, so that because of that, my eigenvalue of Gauss-Seidel is smaller, or you can say the absolute number of the Gauss-Seidel is smaller than the Jacobi iteration, the eigenvalue of Jacobi iteration. So when these things happen, you can say when these things happen, that means the Jacobi iteration can converge faster and more stable. Okay, so if the eigenvalue, okay, if the eigenvalue is closer to 1, that means you converge is slower and it's still stable, but it's just slower. Closer 1 means it's still smaller than 1, but it's closer to 1, that value. If the eigenvalue is closer to 0, that means the converge is faster and also stable. So that's why in the beginning of the Gauss-Seidel iteration, I mentioned that the Gauss-Seidel is converge faster and the more stable system as compared to the Jacobi iteration because of the eigenvalue analysis of their error matrices. And we will show in my lab examples to compare the Jacobi and the Gauss-Seidel iterations steps as well as the eigenvalues. Okay.